Okay, good evening. As a member of the United Nations Association USA Orange County chapter, who has taken special interest in climate change, I was invited to moderate this very distinguished panel. So before I introduce the speakers, let me mention very briefly the role the United Nations has played in climate action. We want to think global and then local and focus on our region. The knowledge of carbon dioxide's greenhouse effect dates back to the 19th century. Can you believe that? Already in the 19th century they knew that. Yet it was only 28 years ago, in 1988, that the Congregational testimony of climatologist James Hansen brought the problem to the American consciousness in the United States. That same year, the United Nations Intergovernmental Panel on Climate Change, or the IPCC, was established. 6 years later, after the recommendation of this international panel of experts, the United Nations Framework Convention on Climate Change began its work. And 3 years later, the first attempt was made to rally the world to climate action via the Kyoto Protocol. For reasons I don't have time to go into here, that was very unsuccessful, but many of you, I'm sure, know some of the reasons why. The United Nations facilitates negotiations, as humanly imperfect as they may be, to reduce war, poverty, illiteracy, ill health, injustice, gender equality, and environmental degradation. That's a big, big task, and that's just, I think, a partial list on it. Last year was a critical and ambitious year, when in September, the member states signed the Sustainable Development Goals. I especially liked the emphasis on sustainable. And in December, they reached the United Nations Paris Climate Accord. The Climate Accord's achievement is the global recognition of the planetary threat that we face, and the establishment of an organizational framework to combat this problem, to create a global response. In addition, it facilitates a multitude of collaborative efforts outside the UN formal framework, where all levels of government, organizations, corporations, nonprofit organizations, all can cooperate for the same purpose. And that is a big part of it. Now, the job of the world community now, our job, and I really mean our job, is to make it work. To pressure our leaders and to pressure ourselves to increase efforts to the levels required to truly reduce climate change. Hopefully, in our discussion with these panelists, who will describe some of the challenges we face, we can clarify what we might do at the local level to hopefully, or to be more hopeful actually about solutions, because sometimes it can be kind of daunting, the magnitude of the problem. So for the hour, here's the plan. Our distinguished speakers will each talk for 20 minutes, after which we'll have a question and answer period. So please save your questions for that time. I believe there's a young lady who's going to pass out little pieces of paper, and you can write down your questions, either just to remember what they are before you forget them with the next topic, or you can pass them down to her by the time of the question and answer period, so that you can read them out if you don't care to speak up. Okay. So before I introduce the panelists, we want to know more a little about you. I think I know some of you already. But nevertheless, I'll ask the questions because I don't know everybody. So please listen to hand raises, okay? How many of you are concerned about the current California drought? Just about unanimous. Most of you, okay. How many have found that water conservation is really a big challenge? Okay, Everybody doing their part? Okay. How many do you live along the coast? Close to the coast? Maybe within a mile or so. Okay, not so many, okay. And, or maybe some of you relate very closely to the marine environment. No, no big fishermen, no yachters, okay. And how would you rate your feelings about climate change? How many of you are not concerned or very mildly concerned about the climate? Don't be shy, it's okay. No. Very few, okay. Some of you are worried? Some are worried, okay. How many of you are alarmed? And how many of you are climate activists in some form or another?
Let's go climate change!
Okay, so now we know a little bit about you. That's great. Now to our distinguished speakers. They have agreed to share their area of expertise on climate and our most precious planetary resource, water, starting from a global view and bringing it down to the regional level. The Pacifica Institute stated quite well our panelists' credentials in detail, so that gives me the liberty to make their introductions a little bit briefer. Okay, so who's going to go first? I think Dr. Jere Lipps. Very good. We'll start with the water. That's where life began, right? So Professor Jere Lipps is Professor Emeritus at the University of California, Berkeley. He's a geologist, paleontologist, and marine biologist. He has taught climate change for over 5 decades. He has researched the impact of climate change upon marine environments and its life forms through time. He has traveled in well over 100 countries where he has seen the consequences of climate change, both in the fossil record and in the current life, in the present. Recipient of many awards through his career, he also has the distinction of having an island in Antarctica named after him. So I'll withhold Professor Feldman's introduction to us. Is that okay? Okay.
So I'll start by talking about the water in the oceans. That's 71% of the Earth's surface is the oceans. We don't hear a lot about what's going on out there in the ocean because it doesn't seem so obvious. But it is a major thing in the oceans that affects us. And here's the 3 areas that I want to talk about because these are the 3 biggest ones in my opinion. 1 is the warming seas. 2, the chemical changes that go on in the ocean as a result of CO2 and this rising sea levels. All of these have their fundamental basis in CO2 increases in the atmosphere. So I'd like to start right there with this slide that shows the increase from 1860 to roughly 1953 or 4, and that's data taken by measuring CO2 in the air bubbles that are trapped in ice that they've taken in cores, chiefly in Antarctica. And then on this side, this is the data that was started to be measured in 1958 by the Scripps Institution of Oceanography people at Mauna Loa, Hawaii. And you can see here how that fits together with that. And then it just continues on up. And although this chart ends at 2,000, we're now at over 400 parts per million CO2. Jim Hansen, who Virginia mentioned, said 350 is the limit. Shouldn't go past that. We're past that. We have to do something. So what does that increase do to the surface average temperature? This is the average temperature for the globe. So do not pick up a snowball here and throw it at me saying this proves global warming didn't take place. It's the average over the entire globe. Is the surface temperature average value from these 4 different places, from NASA, NOAA, the Hadley Center in the United Kingdom, and Berkeley Earth. I put that one on there because Rich Muller, the professor who does this, is not only a colleague of mine, and we have little debates about this on the Berkeley blog, but he was a denier. He said that this temperature stuff is a bunch of bunk. So he went out and got money to do a study from the Koch brothers. But he was a good scientist. He gathered all this data, and this is what he got. And he said, voila, it looks like human emissions are the cause. And we know they're human emissions because this temperature curve tracks the CO2 curve. And we know that the CO2 that's been added here is rich in carbon-12. Why is that important? Because photosynthetic organisms, trees that make up coal, the phytoplankton that make up oil, photosynthesize, and photosynthesis uses lighter carbon more readily than it does carbon-13, which comes out of volcanoes. So that's a signature then that this is a human emission. So how does that then affect the sea? Well, the seas pick up maybe 80–90% of the heat that's reflected or that's re-emitted from the CO2 in the atmosphere, partly because the oceans are so big, but also because they are the oceans are very competent, as we say, in holding that heat. So the oceans are warming, and this has been demonstrated most recently by a great paper in Science magazine in which they had 20 million measurements made by buoys that go up and down in all the world's oceans. And they go up, they send all the data, they go back down, they get a new set of data, and they come back, and 20 million measurements, and it shows definitely where the warming in the oceans is and how the heat gets transferred into the ocean. And at depth, for example, you'd think that the surface water is warm, and that's true. But other things happen there. For example, the salinity goes up because of evaporation, current patterns, and then that warmer water becomes heavier because now it has more salt in it, and it dives down. So that now we're getting depth warming as well as surface warming. What does this mean? Well, at the surface, it'll decrease because the surface currents are driven by the thermal gradient in the oceans, and as that deteriorates, the current speeds will slow and the oceans will become less heterogeneous. Fewer or disturbed water mass boundaries, less upwelling, and so forth. And also, it melts grounded ice. So all of these factors are important. Warming seas then reduce productivity because phytoplankton needs the nutrients that are provided by upwelling, which is now decreased. And of course, the phytoplankton are eaten by zooplankton, which are eaten by fish, so that we messed around with the basic fundamental food pyramid at the very bottom of it, the phytoplankton. Because you eliminate habitats and physiologically disturb the animals and plants, many of them die. And we redistribute them in new patterns. This is happening on land as well as in the sea. So here's a picture of a humpback whale and my former student Vicky swimming with it. This is the top of the pyramid. This is the shortest food pyramid in the world, other than when we eat cows. So the whales eat fish or krill, and those organisms eat the phytoplankton. 3 levels. That's like us. Grass, cows, weed. Those are 2 short pyramids.
Not all.
And here's the chemical changes then. As you put CO2 into the ocean, it forms carbonic acid so that the oceans are becoming less basic and more trending towards acidification. And at the same time, warming water holds less oxygen, so the oceans become anoxic without oxygen, or low values of oxygen. And all of these things point to disruption of the biota. In fact, the 5 major extinctions we see in the fossil record that I studied are all related to these factors. And there's another 25 extinction events in the fossil record over the last 500 million years. And every one of them, so far that we've looked at in detail, and that's quite a few, are associated with rapid CO2 emission by volcanic activity. Massive volcanic activity. So what does that acidification do? Well, amongst corals, it causes bleaching, and corals have photosynthetic algae in their tissues, which give them color because they have photosynthetic active pigments. And those algae leave or are died off, and then the coral dies back off as well, and we've lost a huge percentage of our coral reefs already from this factor, to say nothing of the others that we see. Here's some of this phytoplankton. These things are called coccolithophorids. Each little plate is on a single-celled alga. It photosynthesizes. These are made of CaCO3, very sensitive to acidification. And these are very small, tiny things. So what difference does that make? Well, this is another way to get rid of the phytoplankton, but it also does other things. For example, here's some oysters. Acidification is not going to affect this big oyster. Well, not anymore, it's dead. It's fossilized. So I brought you a fossil oyster, and what I want you to look at is that although this is a massive adult oyster, as a larval part of it right here, very thin shell. And they can't even get past that anymore along our own local coast, I'm told, because that is being dissolved. And that causes problems. Here's another one that we eat, these scallops. And you can see this quite clearly, that right down there, there's a tiny, tiny little shell from which the rest of the shell grew. This shell won't dissolve probably in the ocean that way, but that little tiny fragile one will. So if you like seafood, you might be in trouble too. So what about sea rising? Well, I want to show you a little bit about what we know about previous raises of sea level and look at the ice age. Then we want to look at melting and collapsing of ice and then how that affects sea level rise around the world. So this is the last 780,000 years of temperature record and sea level record in the world. This is the world chart. So you can see here we are today, sea level is at 0, rising though. This is 125,000 years ago. Sea level was 8 meters above what it is today. And that was due not to the emissions of CO2, but due to other climatically controlling forces that we call the Milankovitch cycles. It's a cycling that has to do with the shape of the orbit of the Earth and the tilt and where the equinoxes are in that. So if you look at this chart, everything up here is an interglacial and it's warm. Everything down here is glacial and it's cold. Everything up here is towards normal sea level. Everything down here is as much as 400 feet lower than it is today. So these then have provided us with a history. This is all based on deep sea cores and ice cores. But we knew about this back in the late 60s. That's when I first started studying this stuff. So let's see what it looks like. Here's the 125,000-year-old sea level stand in the Azore Islands out in the middle of the Atlantic Ocean. And you can see it there. And you can also see it here at Laguna, along our own coast. So notice this right there is the 125,000-year-old sea level platform. It's a beach that goes back a ways. It's been eroded out through there, and it continues over here. And if you go all the way to Dana Point, you can track it. You can see it. Next time you go whale watching, watch the shore. So the other interesting thing is that a lot of these houses are built like this, all on one level. Those are former sea levels too, and they love to build houses on those areas because it's flat. So those areas then represent other, usually older sea level stands. Here's Upper Newport Bay. This is the 125,000-year-old sea level stand. Back here is what I call Fantasy Island. And it's built on this platform, which is an old sea level sea bench. But it's been uplifted because the San Joaquin Hills are going up. And it's now, rather than at about 27 feet where it formed originally, this is now 60 to 80 feet in elevation because of the rise of the San Joaquin Hills, which you can see in the background. And again, notice the houses all built on nice level lines. There's 8 different sea level stands on those hills, starting with one actually down here and going to one up there that's over 500,000 years old. So that's the record we see. We know that sea level has done that in the past. And it's also been lower. 13,000 years ago, during the glacial period, when so much seawater was tied up in ice, it lowered sea level to about 400 feet below what it is today, and the coastline would have looked like that. Newport Bay would have been a river valley, and the Santa Ana River would have emptied out here and dumped into the ocean right along there. The Laguna coast, all the way down to Dana Point, is not too far off of where it was 13,000 years ago. So from 13,000 years to about 4,000 years, 9,000 years of sea level rise as the climate warmed to reach the level that we have today. That took about 9,000 years. You can calculate how fast that went. So now that shoreline is here. The sea is still rising. And here's there's 2 reasons. One is that as the oceans warm, the ocean's water expands. We call that the thermal expansion of seawater, and that will give, by the year 2100, an estimated 1.5 or so meter, which is about 4.5 to 4.8 feet of higher sea level, just based on warming the ocean. In addition to that, we add ice from glaciers. Here's Glacier San Rafael that I visited in 2009, and at that time, it had been here, and there it was back there. That's about 100 meters or so, and it's retreating and has retreated even further. It's got about 20 more years before it's all gone. And all of this ice is grounded on the land and not in the ocean, so it will raise sea level. That's just one example. If we go to Antarctica, remember Antarctica, you look at the globe and you think, oh, it's a little tiny place. It's 1.5 times as big as the United States. And it's all covered with ice. And a lot of that ice is grounded on the land at levels below the sea level. So the ocean can seep in underneath there as it warms. And this is West Antarctica over here. And this is the part we worry about. This is East Antarctica. That's not going to collapse for hundreds of years. This one may not either. But it's so difficult to model this stuff because we can't see all the dynamics going on, like warming water coming underneath that causes the ice to melt on the bottom of these big supporting glaciers that hold up all the ice. When they get loose, then the whole thing comes collapsing out. It doesn't melt, it collapses. And I think that's the big deal. Melting is...
So it's a bad situation. What is very surprising to a lot of people when we show them these figures is that the highest per capita water use in California is in the lower Colorado desert, where the last time I checked, there wasn't much water. But there is a lot of agriculture in the Imperial Valley, and there are a lot of golf courses in the Coachella Valley. And that's also a type of irrigated agriculture, as many of you know. If we were to take California and play around with the map of California a little bit in terms of the way a hydrologist might view our state, we would get a very funny looking geography. What we would see is this. Most of the water in our state comes from the north, in particular the Sierras. The snowpack on the Sierras is actually the state's largest reservoir. Okay? That snowmelt through spring, summer, and early fall is basically the California water supply that we drink here in Southern California. We also get a significant amount from the Colorado River, but most of the flows go north to south. Most of the state's water is in the north, it's used in the south. Most of that flow is away from the mountains and pristine rivers and toward farms and cities. My students often ask, what about desalination? Well, aside from all of the other issues associated with desalination, which we perhaps will have the opportunity to discuss in the Q&A, is the fact that California's plumbing system moves water from the north to the south and to the coasts, and from the Sierra to the coasts and to the Central Valley. Desalination means we would have to pump that water uphill, okay? It's the only way agriculture is going to get it. It's the only way interior cities are going to get it. One other thing about this figure, the flow of water in California is not a result of geography. It's a statement about political power. The reason we move water from north to south and from the Colorado River primarily to Southern California is because, as William Mulholland, a great water engineer who built the LA Aqueduct, noted several decades ago to an understudy, water does not flow downhill, it flows toward money. Okay? And here in Southern California, most of our water, as I think all of you know, is imported. Here's the California Aqueduct, which takes water from the Delta. Less of it each year because of climate change and also because the fish in the Delta need water every day. We can go a day or two without it. The LA Aqueduct, the Colorado River Aqueduct, and significantly, as we're going to talk about momentarily, there is a good deal of effort going on in conservation and in groundwater use and also the recycling of wastewater, but not nearly as much as we need to do. And one of the things I want to pitch tonight, and this is why I said there's bad news and good news, is because we have to adapt, we can, but we have to get out of this habit of thinking that there is such a thing as wastewater and drinking water and storm water and other kinds of water. It's just water. And we have to figure out a way to use, conserve, and reuse every drop. All right, there's the drought, and it's something to worry about. If you look at a 5-year period from 2010 to 2015, you can see the tremendous shrinkage of the Sierra snowpack. And it can also be chronicled over a period of time. Yes, this winter has been better, but over the past 4.5 years, it is estimated that the diminution of this snowpack would be the equivalent of 4 Lake Meads, okay? So it's going to take a lot of snowpack, and it's going to take a lot of rainfall, and it's going to take a lot of restoration of rivers and streams to get California back to where it needs to be to serve the needs of 38 million plus individuals. A question that's often asked is, how bad can it get? These are pictures taken at Lake Mead last June. If this lake level were to fall anymore, and it looks like it won't, at least for a while, thanks to the El Nino storms that we have had in the northern Rockies. But if Lake Mead were to fall a few feet more, they would be unable to generate power at Hoover Dam. Okay? So that's one result. Water and power, very closely connected. And when we talk about climate variability and drought, we also have to talk about climate variability and flooding. The models that have been generated by the Intergovernmental Panel on Climate Change and other organizations suggest very strongly that what we have been seeing in the western United States for the past few decades, and what we're likely to see increasingly in the future, are more intense droughts punctuated by periods of very intense short rainfall. If, and this is one of the things that's underscored in this figure, if we could capture this, which we can't yet, because we do not have the infrastructure, and as a political scientist, I would argue we also lack the political will. But if we had both of those things, we could capture enough water in a given year, in a good El Nino year like this, probably to satisfy about 800,000 homes in the city of Los Angeles alone. So that's a lot of water, and it can be harvested. There are ways of storing it. So, drought punctuated by periods of flooding, intense rain events, storm events. Somehow or another we have to adapt to this. Question is that often arises, but aren't these short-term problems? And again, the models would suggest they're not short-term problems. Last summer in August, a couple of colleagues of mine from Davis, UC Irvine, and the National Oceanic and Atmospheric Administration wrote a paper that was produced out of a conference we put on that was published in Nature. There's no way you can read this text, I appreciate it. But the point is this text on the left underscores what we found. Basically, we argued that these are not short-term problems. They are recurring events that are likely to become more frequent due to climate change. And if that's true, then the problem is how we use and manage the water we have. The argument is that sustainably managing the problem entails meeting our needs while also protecting the environment. And how do we do that? 4 things: reducing demand and avoiding profligate and wasteful uses. That means we really have to rethink the way we value and use fresh water in California. We have to become much more efficient in our use. We have to reuse every drop of it, and we have to harvest wherever possible new sources. We label this phenomenon, and we're not the only ones that have done this, anthropocentric drought. That is to say, the drought, while caused by natural forces, in quote, are exacerbated by human activities that worsen drought and worsen the impacts of drought. That's what we're dealing with. So what do we do about this? Well, the question that often arises is how worse can things get? And the answer is they can get pretty worse, and probably will. One of the things that this map shows, which was generated a couple years back by the Public Policy Institute of California in San Francisco, is that the areas that you see in darker shades of red are areas that have higher demands for precipitation or higher demands for water because of either irrigated agriculture or lawns. These are urbanizing areas, whether it be the desert portions of California here, the Great Basin here, but these are areas in which the summer water requirements for turf grass in monthly gallons per square feet is very high. The problem is that urban water demands in these regions, in what we call the Inland Empire, are growing. At the same time, we are becoming more efficient in water uses in coastal communities, especially communities like Irvine. They are not becoming more efficient in the inland regions. And most of the growth will be in hotter inland counties with high evapotranspiration rates that are going to be exacerbated by climate change. So it can get worse, and I'm sorry to say, it very well might. reuse, and conservation are about the middle range of this, but some cities reduced as little as 4, as much as 36%. Most utilities have complied. There's been tremendous efforts made in public information, outreach, in some cases arm twisting to get people to use less water, or mandated water reductions. But a few communities have been fined for missing targets. Not surprisingly, communities that are either very affluent or very, very water dependent, or both, and have unfortunately taken the attitude that if we can afford to pay for it, by gosh, we're just going to keep using it. Even with a strong El Nino, the deficit from the norm is enormous, equal to the entire flow of the Colorado in a good year. And we haven't had a good year in the Colorado for some time. Environmentally, some native fish species have been virtually wiped out, and it's going to take years to recover from this drought. And we don't know if the behavioral changes in response to this drought will last. When California's had droughts in the past, even though the mandated restrictions have not been as rigorous as what we're experiencing now, there were certainly changes that occurred, but they lapsed back to old patterns once the drought was over. This is the wild card. This is the $64,000 question we don't have an answer to. Water use reductions. I just want to say a few things about this. I mentioned Irvine Ranch Water District. It's done a pretty good job of reducing water use quite significantly, particularly residential use. And when you compare Irvine to other cities in the region, extremely well. Residential use in nearby districts varies tremendously. We can make some preliminary assessments about these policies and how well they work. We do know the residential use varies from community to community. Penalties for overuse are not evenly applied. There have been many questions that have been raised over equity and fairness in the measures that have been taken in California to deal with the drought. And as a political scientist, I think they are justifiable concerns, because not everyone is pitching it equally. We also know that shaming or outing, you've seen and read reports of this, it doesn't work. It's unfortunate. It makes us feel good. It's kind of a cathartic effect. But the evidence suggests that public exposure may have unintended consequences. This is a fellow in Beverly Hills that's gone around and outed people who profligately used water. And I love the bottom line here. Not everyone is happy about what he's doing. One woman, quickly tiring of Corcoran's lecture on conservation while she watered her plants, turned her hose on him. So, of course, maybe that saved the shower that day. At any rate, what works? Conservation rates work. Rates that charge people more for using more water. Water smart billing systems work, showing residents how much water they use compared to the average and efficient households can be a strong incentive to conserve. And people want to be in line with their neighbors. But there are longer-term options, and I want to finish up by talking about some of these. Question that's often asked, certainly my students ask, can we reuse wastewater? Well, we have been doing it for millions of years, as you can see. By the way, Madeline Walsham, the student on the left, this was taken at the Fountain Valley groundwater replenishment system plant. She's doing fine, by the way. She was drinking the recycling water. I've been in touch with her. She's doing great. Public acceptance, however, is an issue, big issue statewide. Here we see the governor satisfying his thirst at the Orange County replenishment system plant. We have to consider the fact that California has a very diverse population, and we have a legacy of environmental injustice. And these issues have to be addressed if you're going to widely use wastewater reuse as a way of meeting the needs required to adapt to climate change and to drought. So we need to give the public all the information on available options and allow them to evaluate and compare them and their long-term consequences. Finally, quickly, rainwater capture and low-impact development. Los Angeles has been doing it for the past 5 years. It was established in a partnership with community groups and the building industry, which was a smart thing to do because you want to get the buy-in of people that are actually going to be responsible for implementing these measures. Does it work? Well, it looks good, and it works somewhat, but it's way too early to tell how much water is really being harvested and reused, and whether or not this kind of landscaping will be maintained. That's the bottom line. Research that we've done, my colleagues and I have done in Australia, show that there has to be a big buy-in by communities to make this work. A lot of potential for stormwater capture. Surprisingly, enormous opportunities here in the Southland. It doesn't rain very much, but when it does, you know, as I often tell my students, we worry when it doesn't rain, and we worry when it does. Finally, this is something that we came up with some collaborators in Australia. This is our long-term ideal, and we simply call this water-sensitive development. If you take various literatures that are coming out on water reuse, recycling, conservation, what you can do is take the existing urban form, and you don't completely throw it away and replace it, but what you do is you build on it. You develop ways of substituting fresh water for things that don't need fresh water. We can reuse wastewater in the house, okay, for various things. We can also regenerate water. We can do it through biofilters, for example, which will actually capture rainwater, filter out some pollutants, and replenish groundwater systems. And we can conserve and reduce use. That doesn't mean we do away with drinking water plants or waste stabilization ponds or wastewater treatment plants, but we take this old infrastructure and we add these new wrinkles, centered on the household as a way of dealing with things. This is something that can work. It is being done in places like Australia, and it can be done in California. The future? Well, prediction is difficult, especially when dealing with the future, as a Danish proverb tells us. Let me leave you with a couple thoughts. If we're serious about confronting climate change, we have to recognize it as a long-term challenge, and it's one that's likely to worsen given our growing population and our already existing conflicts over water. Anybody here deny that we have conflicts over water in California? Very good, thank you. 3 critical questions we need to consider. Is our denial of climate variability new, or have Californians always been deniers of climate on our ability to prevail? Rain will follow the plow. That was an aphorism that was often used when the West was settled. It was wrong then, it's wrong now. Does population growth drive water demand, and should we seek to limit growth? Or has inexpensive and subsidized water spurred population growth and profligate use? If that's the case, that's my personal belief and others, then we need to consider the value we place on water, and we need to induce changes in behavior. So this is what we should do. This is what we do and should not do in the future. So with that, thank you very much.